Energy is all around us, from the electrical energy to turn on our lights, to the chemical energy in our food. But today, we're here to talk about thermal energy. My name's Valerie, and I'm the Outreach Coordinator for Future Energy Systems, or FES. FES is a research program at the University of Alberta focused on studying the energy transition. So what is thermal energy? Well, it's the energy associated with a change in temperature, and this change can impact the object. For example, in this kettle, I am heating up the water to make a cup of tea. Heating up the water is making the molecules move faster and faster, so they have more energy. And we can see this steam, which is a change of state. But as delicious as this cup of tea is gonna be, what does it have to do with the energy transition? Let's explore. In this part, we'll join Michael, who will explain the basics of thermal energy and how we can use this thermal or heat energy to make other forms of energy that we can use. He will introduce us to geothermal energy and the very cool Stirling engine. Then we'll join Leslie to do some heat energy experiments that you can try at home. Here are the supplies you'll need. Have fun!
Hello, my name is Michael Nicole Cito. I'm a master's student at the University of Alberta, and I'm here today to talk to you a little bit about thermal energy, specifically in the context of mechanical engineering, which is what I personally study. So everything around us in the world has energy, and energy can take different forms. Common examples you might be familiar with include electrical energy or chemical energy, like the energy in a battery of a smart device that you have. It can exist as kinetic energy, which is the energy of things in motion. So think of a fast car moving down the highway. It has a lot of kinetic energy. We can think of potential energy, which is the energy kind of stored in objects in their physical state. So things like an elastic band has potential energy if it's stretched out, or things like a spring. But specifically, I'm here to talk to you today about thermal energy. So thermal energy is really kind of the energy associated with an object that we measure by taking an object's temperature. And so things at different temperatures have different thermal energies. Also, things that are very similar that have different amounts of thermal energy will actually have different properties. So the common one you might be most familiar with is phase. So things that have a lot of thermal energy could be in a gaseous form. When they drop to a lower thermal energy state, they become liquids. And lastly, they'll become solids. So a common example we are probably all familiar with is like a hot beverage, like hot chocolate. So the steam rising off of that is actually in a gas phase, whereas the liquid hot chocolate, which is mostly water, exists as a liquid, common around room temperature. And then again, we're probably very familiar with the solid phase of water, which is frozen. So things like a chocolate ice cream. Those things would have lower thermal energy than the gaseous or even the liquid form of energy that we just mentioned. So beyond those different properties, there's another kind of aspect of it called density, which we'll be exploring a little bit further today with the experiment you're going to be doing. But the way we humans experience thermal energy ourselves when we touch things like a cup of hot chocolate or lick cold ice cream is a specific kind of energy related to thermal energy known as heat energy. So heat energy is the form of energy that is transferred from one object to another because of the temperature difference that exists between them. So when we feel warmed up by a hot chocolate or warmed up by going into a hot outside temperature or a hot room, what we're experiencing is heat energy that is actually flowing from those high temperature things to our bodies, which in this case are the lower temperature object. But likewise, when we feel colder by eating ice cream or going outside on a cold winter's day, what is actually happening is that heat energy is leaving us, and we feel that because our warmer bodies have a higher temperature than the cold substances around us in those cases. So all systems where objects have different temperatures will have heat transfer going on until they reach what is called thermal equilibrium. So it's the balance point where everything is the same temperature. So again, going back to the common hot chocolate example, if you leave that hot chocolate in a cup in a room, it'll eventually cool off until it's the room temperature. Likewise, if you were to leave an ice cream in a similar room temperature, it would gain heat, change phase, and melt until they both existed at the same temperature as the room. So we can actually affect how fast this happens by adding insulation. So a jacket on your person in winter will slow down the heat transfer from you to the environment. Likewise, we can speed up that heat transfer by mixing or blowing on things like you would on a hot drink, and that can speed up how quickly it'll cool off. But we can also change that flow of heat energy into other forms of energy, which is what I primarily study. So, for example, if you take geothermal energy, it takes advantage of the fact that there is a flow of heat energy from the Earth's hot core towards the colder surface of the planet. So we can use heat energy directly, in that case, especially of geothermal, to heat homes or buildings or other things. Or we can turn part of that energy flow into useful energy, typically electrical energy, by using something called a heat engine. And a heat engine is a device that uses science of thermodynamics, which is what I study and specialize in, to convert heat energy into other useful forms of energy. So if you think like a steam power plant or the engine in your car or the engine of a jet plane, all of those things burn the chemical energy inside of a fossil fuel, turn it into heat, and then use that flow of heat to turn it into useful energy that engine applies for. So what I specifically study is a specific kind of heat engine that doesn't use fossil fuels in this case, but can use any kind of heat. In the case that we're studying is geothermal, or things with very small differences in temperature. So the geothermal energy isn't that much hotter than boiling water, but we can still design an engine that takes advantage of that small heat temperature difference and takes a little portion of that and turns it into useful mechanical energy, which we turn into electrical energy. Well, that's the end goal anyways. But in terms of the experiment, and what I'm sure you're eager to get on with, it's your turn to explore heat energy. So in the experiment, you'll see the property or the thermal property of density actually at play. And you'll also be able to see how heat transfer can be sped up or slowed down by taking advantage of that unique physical property associated with thermal energy. And you can even see how that heat flow can be turned into movement or kinetic energy of the water itself through the experiment. So I hope you enjoy.
Hi everyone, my name is Leslie, and today I'm going to show you 2 short experiments using water to explore heat energy. But first, make sure to get your parent or guardian's permission and help before starting. For our first experiment, you're going to need some hot water, a clear container, some room temperature water. You're going to have to make some blue ice cubes the night before. So all I did was put some blue dye and some water and freeze the ice cubes overnight. You're going to need some red or pink food coloring, some blue food coloring, and a little container of some sorts. And in this experiment, we're going to demonstrate how water can have different densities based on the temperature. So remember that first you're going to need to make some blue ice cubes. And once those are frozen and ready to go, you can fill your large container with some room temperature water. Next, you can ask your parent or guardian for some help at this step, but we're going to have to be very careful with the hot water. And what you're going to do is, I have some pink food coloring in here, and I'm going to fill this little container with around 10 drops. After you fill it with the food coloring, you're going to fill it up with some hot water. Now, what you're going to do with the large container of water is you're going to grab 1 or 2 ice cubes and just gently place it to the right of the container. Next, with your little vial of hot water, you're going to gently place it into the water so it flows in nicely. At this step, it's really important that you pour it in very gently. You can almost just put the container in and let the hot water flow out of it. So let's give it a few moments, and what do you see? So after a while, you should start to see layers forming. From the side, we can see 3 distinct layers, with the purple at the top, the blue at the bottom, and the clear layer in the middle. Have you ever seen a slick of oil on water? It kind of looks like a rainbow. Well, that's oil floating on top of water. Oil is less dense than water, meaning it has less molecules in a given amount of space. On a smaller scale, water has different densities at different temperatures. Hot water is the least dense, meaning that there's not as many water molecules in a given area. It has the most space between each water molecule. On the other hand, cold water is denser, meaning it has more water molecules in a given area. So each molecule has less space between them. It's easy to confuse the terms weight and density, so let me give you a simple explanation about their differences. Weight is a measure of how heavy something is in total, but density tells us its mass in relation to its size. While weight would be like just kilograms or just grams, density is kilograms per meters cubed or grams per centimeters cubed. For example, we have 2 bags of rice, and they are the same size. However, one might be heavier than the other. We can say that the heavier one is denser because it has more rice stuffed into the bag. This also means that the denser bag of rice has less space between each piece of rice. So, looking back at the 3 temperatures of water and their densities, we can see that the hot water is less dense, so it floats near the top, while the cold water is denser and sinks to the bottom. You may have even felt this when you've been swimming in a lake. The surface of the water is cooler, but the deeper you go, the colder it gets. The lake has layers of water that form and then mix over the years as temperatures and densities change. For our second experiment, here's what you're going to need. You're going to need some cold water and some hot water. You're going to need 2 of the same glass jars, or you can use glass cups. Get some stir sticks. You need your blue food coloring and red, pink, purple, anything else works. You're going to need a little piece of plastic and a tray to catch any spilled water. So what you're going to do, take one of your jars and fill it with the hot water. Be sure that you fill it to the brim as much as possible. And you're going to add some food coloring into it. And we'll just leave that there for now. Next, you're going to take your other jar and fill it with some cold water. Also make sure to fill it to the brim. And add some of your other food coloring into it. Now the next part is a little tricky and it might take a couple tries to get it right. First, you're going to take your little plastic card and place it on top of the cold jar. The water itself should form a vacuum, and you should be able to flip it over like so without spilling any water, or minimal spilling. Then, you're going to line up the edges of the cold jar with the hot jar. Make sure that it's all lined up around so that no water will spill out, and then carefully slide out the plastic and watch what happens. We can start to see the 2 colors mixing. And after a while, the 2 colors in the jars have mixed to become one even color. This is a good visual example of thermal equilibrium. The hot, or the purple, and the cold, which is the blue, have mixed together to form one even color. Okay, so after you have that all cleaned out, we're going to do it again, but this time we're going to flip the hot and cold waters. So you're going to start with some hot water and put it in the jar again. Next, we're going to add our cold water into the other jar. This time, you're going to take your little plastic card and place it on top of the hot water. Again, the vacuum will form a seal and you can easily flip it over so no water spills out. Again, place it on top of the cold jar and line up the edges so that no water will spill out when we remove the plastic card. This time, pay attention to what happens once you take the card out. After we give it a few moments, we can see that the purple is staying at the top and the blue is staying at the bottom. This time, the hot and cold waters aren't mixing. And why do you think that is? Since it's denser, when the cold water is on top, it sinks right through the gaps of the molecules of the hot water. This caused the blue and the purple colors to mix together. The denser material, which is the cold water, weighs more, so it gets pulled down by gravity. And this movement of heat energy is called convection. Convection is the transfer of heat energy by the movement of a fluid between areas of different temperatures. For example, boiling water. When we boil water, the heat moves from the burner up into the water. Or when ice melts, the heat from the air moves into the ice. Remember that the heat is always transferred from the hotter material to the colder material. On the other hand, when the hot water is on top, there is no mixing. This is because all of the denser, colder water is already at the bottom. We know that the denser water sinks, but since it's already at the bottom, there's no movement or mixing. To put this into perspective, the more thermal energy there is, the more movement of molecules, so the more space between the molecules. And this is why hotter materials are less dense. And this is exactly the principle we saw in our experiment.
How did your experiments go? Hopefully there weren't too many spills. We'd love to see any pictures or hear about your results on Future Energy Systems Facebook or Twitter. Now that we've learned about the basics of thermal energy, geothermal energy, and heat engines, let's join Calynn in the lab to explore these Stirling engines further.
Hello everyone, my name is Calynn Stumpf and I'm an MSc student here at the University of Alberta. A Stirling engine is a machine that is able to transform heat into electricity by a mechanical process. So in the lab where I work, we employ different types of Stirling engines and try to increase the performance of them so that they can produce the most amount of power from the littlest amount of heat. So we in our lab are looking at heat sources from water stored underground that's been heated by the earth to about 100 degrees Celsius. The research that we perform in our lab is important because as the world's population grows, so does its energy demand. And we must look into utilizing power generation processes that do not produce greenhouse gases. And in this case, a Stirling engine fills that niche.
So pictured in front of you is a Stirling engine. So Stirling engines work by operating between a temperature source and a temperature sink to generate mechanical power. So here you can see two different pistons of a Stirling engine, one being the power piston and the other being the displacer piston. The power piston is able to move according to the pressure change inside the Stirling engine, and this in turn drives the displacer piston, which results in the fluid moving between the temperature source and the temperature sink, which generates the pressure change and in turn creates the motion of the power piston. So you can see here on the top view, the actual movement of the power piston is linear in an up and down fashion and is transformed into rotational motion, which then we can connect on, for example, an alternator, and from there we could generate electricity from it. So the spinning disc there is a flywheel. The flywheel is what helps keep the motion of a Stirling engine constant. Here is another version of a Stirling engine, similar to the one we've seen before, where we have a power piston and displacer piston, but in this case, a much larger flywheel. And this flywheel is much larger because the Stirling engine is much smaller in this case. Here we have even a smaller Stirling engine, and you can just see the power piston being driven by the rhombic drive, which are the two red gears. Here is an earlier iteration of one of our Stirling engines that utilizes a significantly smaller bellows for the power piston seal.
In order to determine how well our Stirling engines are performing, we must test them. So this is one of our Stirling engines in one of our testing apparatus, so we can determine the amount of power that it is producing. We also have to make sure that our components are rigorous. And pictured here is what you may know from a Stirling engine. This is called a coffee cup Stirling engine. So it is able to run off the heat from the coffee cups underneath it. In our lab, we primarily use 3D printing in order to create our Stirling engines, as it is both quick and relatively inexpensive. This 3D printer here is quite large, and it can print 1 meter by 1 meter. Stirling engines can be utilized in many applications, such as with concentrated sunlight or even by hot water. So in this laboratory, we're looking at utilizing Stirling engines to create power off of geothermal water that is stored deep below the Earth's crust. And with that, we can help try and mitigate the effects of climate change by having a power generation process that does not rely on fossil fuels.
Isn't that crazy? A Stirling engine that can run off the heat of a hot drink? Thank you so much for joining us to learn about thermal energy. Make sure to subscribe to Future Energy Systems YouTube so you don't miss any of our exciting content, and check out the links below. There's so much to learn as we explore our energy future.